Students, if you are attending for the first time, Dr. Omkar Deshpande is 1 year. He joined IIT 1 year after I joined. Uh, he had a very good rank. I think he said 17. He finished his BTech from IIT Delhi in 2002, if I'm not wrong. He was in a 4 year program in computer science. Then he went to Stanford to do his PhD in computer science again. And it is his passion to teach physics. So it is his sixth lecture. Till now, we have gone through the history of, if you will, development of physics. We largely started with Aristotle. We kept moving forward. In the last class, we had discussed Galileo's new astronomy. And now we are going to be closer to studying what will be very familiar to you. So, Omkar, over to you, and we can start.
All right, so welcome back. I think this is our fifth or sixth session. I just want to take 5 minutes to summarize where we are in the overall progression of physics for those of you who have attended earlier sessions and those who have been following the recordings. So, what we did last time was we saw how Copernicus um, put forth a new heliocentric astronomy that he felt was more elegant than Ptolemy's geocentric astronomy. So Copernicus's model for the universe had fewer epicycles, and it explained the retrograde motion of Mars, without needing epicycles. But he couldn't handle the objections to his model that were based on a combination of common sense, the physics of that time, Aristotle's physics, and the religious texts of that time. And he made no attempt to come up with a new physics to support his astronomy. Now, then we saw how Galileo attempted to find evidence that would support Copernicus's model over Ptolemy's model through telescopic observations of the moon, uh, with its mountains and valleys. Galileo realized that the moon was likely not made of ether, but made of pretty much the same substance that you find on Earth. And neither was the sun probably made of ether because it seemed to have sunspots that were born and which could also disappear after a few days, showing that, changes did happen even in the celestial realm. He also discovered four new planets, or today we would call them the moons of Jupiter, which actually any of you can see through your binoculars if you just looked at, Jupiter with an 8 by 40 or 10 by 50 binocular. Uh, uh, you would be able to spot the moons of Jupiter. Um, Showing and that showed Galileo that there were other bodies in the solar system around which rotation could happen. So the Earth was not unique in that sense. And he also saw that the stars in the night sky were very far away and they didn't get magnified even through his telescope. So that means even a heliocentric universe would have the stars really far away. And so as the Earth goes around the sun, you wouldn't see the separation between the stars increase or decrease across the seasons. We discussed stellar parallax last time. So Galileo argued that, well, there should be no stellar parallax even in a heliocentric universe. So that wasn't really an objection to Copernicus's model. And then he saw that Venus, the planet Venus, went through a full set of phases like the moon, which showed that it actually was sometimes behind the sun, sometimes in front of the sun, sometimes on the side, showing that it basically went around the sun. And Galileo also poked some holes in Aristotle's physics by supposedly showing, probably a legendary story, but supposedly showing through an experiment from the top of the Leaning Tower of Pisa, dropping two balls with very different masses, and showing that the heavier and the lighter mass almost land at the same time, right? The heavier ball landed maybe slightly earlier, but Aristotle had claimed that the heavier ball should fall with a much higher speed towards the center of the universe or the center of the earth than the lighter ball. So that was one of the defects that Galileo exposed. But Galileo overall could not convince his audience that Aristotle and Ptolemy were wrong, or that Copernicus was right. Uh, his attempt to answer the religious objections by reinterpreting the Joshua passage from the Bible in favor of, a heliocentric model, landed him in trouble with religious authorities. We saw that last time. Nobody was willing to accept his most important argument that the tides could be explained only if the earth was moving, like water, sploshing around when you move a tub containing water. And even the full phases of Venus, even though that observation refuted Ptolemy's model, it couldn't refute more complex geocentric models, such as uh, the model by Tycho Brahe, in which Venus did go around the sun, but then the combination of Sun, Mercury, and Venus went around the Earth. So he couldn't refute that kind of geocentric model. So he couldn't really prove heliocentrism to be correct. Um, so Galileo's attempt to therefore ridicule the Aristotle-Ptolemy system overall backfired, and he ended up making his old friend, who was now the Pope, feel angry and betrayed when he published his most famous work. Um, he was forced to publicly disown his belief in Copernicanism, and he was put under house arrest for the remaining years of his life. Now, during those last few years under house arrest, Galileo found time to start building up a new physics. And remember, we've talked about this in the first session, that physics is the study of nature at its most simple and fundamental level. And at its most fundamental level, let me write this down. Any change that we see occurring in nature, any change, any change in that we see occurring in nature um, involves the motion or movements of small particles, is due to the motion or movement of small particles. There were ancient Greek philosophers like Democritus who called these particles as atoms. The word atom literally means that which cannot be cut or divided. Um, but Galileo didn't really develop an atomic theory, but he did recognize the importance of studying the motion of particles, because if we can describe, if we can describe how this happens in the language of mathematics, then we can predict what will happen in the future. Then we can predict uh, basically the positions of all these small particles in the future. In other words, we can predict the changes that would happen in the future. In other words, we can predict the future state of the universe. We can predict the future state of the universe. This is why the study of motion is so important and fundamental in physics. It allows us to predict the future state of the universe if we can succeed in building a science of motion. So this study of motion is called mechanics. And it became the focus of Galileo in his last few years. He tried to describe how motion happened using the language of mathematics. And once you have an accurate account of how things move, for example, how things fall naturally, free fall, and other types of motion, uh, remember that, he felt that Aristotle's followers didn't have an accurate account of motion, right? That's what the Leaning Tower of Pisa experiment exposed, that they didn't really know what they were talking about. So you need an accurate description of motion first, then you can figure out the true causes and mechanisms behind that motion. So mechanics uh, is thus something we can divide into two phases. In the first phase, we are simply describing, right? Describe what we see. describe the motion we see in the language of mathematics. Language of mathematics. And this subfield of mechanics is called kinematics. And that was the focus for Galileo. First, you need to uncover nature's kinematics before trying to come up with explanations for why things move the way they do. So the word kinema just means motion, right? So for example, the word cinema in English is actually from the same root, because cinema is about watching pictures that move, motion pictures, right? So that's what movies are. So that's kinematics. Um, Now, unearthing, so describe motion in the language of math, and then after you've done that, then unearth the you can say the causes behind motion, behind that motion. Why motion happens the way it happens. And that subfield is called dynamics. Galileo made a little bit of progress there, but not much. Kinematics was his main contribution. But you cannot build an accurate dynamics without an accurate kinematics that you're trying to explain. So Galileo developed the kinematics for the terrestrial world, how things fall, how things move on the Earth. Kepler developed the kinematics for um, the heavenly realm, right? He found, for example, that the reason why people are stuck with epicycles is because they are wedded to this notion that everything in the night sky has to be a combination of circular motion. If you give that up, and if you allow other shapes, other curves for the trajectories of the celestial bodies, like ellipses, for example, ellipses, hyperbolas, and so on, um, then you get a much more accurate fit to the data without complicating your model, right? So kinematics, I would say, was mainly the contribution of Galileo, and you can say Kepler. Dynamics was developed mainly by Newton, building on top of Galileo and Kepler's kinematics. Without that, Newton would not have been able to, do what he did. By the way, the word mechanics uh, also has a second meaning in English, right? One of the other meanings in English is, um, so I'll just make that a side note, that mechanics here, here means in this class, is not equal to the other meaning. What's the other meaning? The construction, operation, repair, and maintenance of machines. The construction, operation, repair, and maintenance of machines. Like when we talk about a car mechanic, you're talking about someone who knows how cars are built, how to operate a car, how to repair a car, how to maintain a car. We are not talking about this meaning here, right? So one of the important things to remember in physics is many times you will see that in physics, the same words appear that we use in the English language, but the meaning in physics is different. And if you don't keep in mind the specific meaning of the word in physics, you will get confused. That is part of the reason why students have difficulty in physics, because they just try to think intuitively about work, about energy, about um, acceleration or whatever other quantities physicists define, without realizing that there is a very specific definition to everything in physics. So mechanics is the study of motion. It's not about what car mechanics do. So keep that in mind. Now, how do we begin a study of mechanics? Naturally, we have to begin with kinematics first. So how do we begin kinematics? So in the real world, we are living in three-dimensional space, and so motion in general can be 3D or at least 2D in our daily life. But we are going to begin with kinematics in one dimension first. And the reason why we will stick to 1D kinematics initially is if we understand how motion can be described along a straight line in one dimension, then the mathematical tools that we develop to describe that motion can be easily generalized to 2D and 3D, right? Just for doing 1D kinematics, you are going to need sophisticated tools. You'll need to recall all your algebra. You need to recall all your geometry. You need to understand the fundamentals of calculus. Then when you extrapolate that to 2D or 3D, then vectors come in. So if we directly jump to 2D or 3D kinematics, you will have to deal with both vectors and calculus together at the same time. It's not a very good idea. So let's do it in a way that the tools are developed one step at a time. You get comfortable with them, and then we go to uh, you know, uh, the next set of tools, which use the tools that have already been built. But at the same time, we know that 1D kinematics is not something unreal, right? For example, um, how do heavy elements fall for Aristotle? Essentially, free fall motion is motion in a straight line. So we are already talking about something that's very real. Galileo's legendary experiment from the top of the Leaning Tower of Pisa was about motion in a straight line, the motion of a falling object. So by understanding 1D kinematics, we can actually begin to describe how things fall or move in a straight line in the language of mathematics. So we'll start with simpler case studies before moving on to more complex case studies. Because if you directly jump to something that's complex, it will feel too hard and then you will feel like giving up. The reason why we give up any field of study is because we directly encounter something that's too hard for us. You remember the story of Goldilocks. You know, she could sleep only in a bed that had the right size. If it was too big, too small, wouldn't sleep. She needed porridge that was of the right temperature. Too hot, too cold, wouldn't have it. In a similar way, when you are trying to solve problems, you need problems to be in your Goldilocks zone, that is just the right level of difficulty, where you are, right? And it depends on where you are. Different people are at different starting points. So if it's too easy for you, you'll get bored. And if it's too hard for you, you'll feel like giving up. You'll feel checked out. So in both cases, whether the problems are too easy or too hard, you'll feel like, you know, this is not a good use of my time. So they need to be in the Goldilocks zone. And this is why teaching a class with 50 people, let's see how many, 52 people, uh, each with a different background is very hard. It's almost like an impossible problem to solve. How do you cater to people whose starting points are different? Because everyone's Goldilocks zone is different. Okay. So we have to acknowledge that limitation. Okay, it's not about the teacher being bad. It's not about the student being unqualified. It's about the nature of learning, the way the brain learns, the way we feel motivated to learn is when we encounter problems or questions that are inviting, interesting. At the same time, they should be at the right level of challenge for us. We should feel internally that, okay, I'm going to succeed maybe if I try this a little. All right, so what's 1D motion? 1D motion happens when a particle, so we can say any motion for that matter. Motion happens. I'll just write this simple sentence in English. motion happens or any change in nature happens. See, ultimately, like I said, for some of the ancient Greek philosophers, any change in nature that you see in the world around you is because atoms or particles of some kind are moving from one place to another. If there was no motion, the universe would be frozen. So, understanding motion gives you the key to unlock how the universe works so that you can predict the future states and maybe even the past states. That's the hope, at least. So, motion happens when a particle changes its location, we'll call it position, over time. So, we need to focus on these three words: particle, position, time. When a biologist looks at an amoeba under a microscope and sees it move, right? You know, right, that amoeba have these pseudopodia. Pseudopodia means false feet. They don't have a rigid fixed shape. Their shape keeps changing as they move. Macrophages and other cells of the immune system also, they'll swallow the bacteria and so on. So when you see cells move under a microscope, changing their shape, um, it's very difficult to identify where is this amoeba or where is this cell. If you were asked to identify a point where where the cell is, which location is it are we talking about? It's hard because the thing is changing its shape. So we have to make things simple to start with. And so we will start by assuming that we are not dealing with objects like cells that can change their shape. We are dealing with particles. So a particle is nothing but a point mass, which means we can show it as a geometrical point with a well-defined location, infinitesimal in size. So there's no ambiguity about where the particle is located in space, like an amoeba. And once we develop the physics for handling particles, we can then extend it and ask, how does this apply to masses that have an extended shape, a shape that is spread out in space? How does this apply to particles that can change their shape while they are moving? Like even an athlete a high jump athlete uh, who jumps over like a horizontal pole, they're changing their shape. A swimmer who dives into water from a diving board, they're changing their shape as they're moving. So that's harder to analyze. But if we can develop the physics for point masses, then we can extend it to more complex objects. So, so we are talking about point masses, okay, particles, and moving along a one-dimensional line. Now, the 1D line could be a horizontal line or it could be a vertical line, right? But since we want to use the language of mathematics to describe the 1D motion, we will assume that we are superimposing a number line on top of this 1D line. So you're familiar with the number line, right? The real number line. So we will assume that we have a number line that we superimpose on top of this one dimension, whatever dimension, whether it's horizontal or vertical or in some other direction, so that every particle, if a particle is somewhere here along that line, it gets assigned a unique location which we can describe as a number. All right, so this number, whatever this real number is, this real number is the position of the particle. So whenever we talk about the word position in physics, we are assuming that there is a number line, or when we move to 2D and 3D space, there will be two or three number lines that are perpendicular to each other, forming a coordinate system. And the location or the address of the particle in that space, given by one number or maybe two or three numbers, is going to define its position. Now, what numerical value this is depends on how we superimpose the number line. If the number line had been put in a way that 0 was somewhere further to the left, then this position value would have been bigger in magnitude. But since when studying motion, we are talking about changes in position over time, we don't really care about what the absolute position is for the most part. Right? We are going to care more about changes in position than about position itself. So it's okay to put the origin wherever you want, as long as it makes your calculations easy. Right? And this is truly about making calculations easy, not like Copernicus and Galileo, or the objectors to Copernicus and Galileo, who thought that, well, use the heliocentric model to make your calculations easy. It's not true, though. Well, here we are meaning something like that. Take whatever origin you want. It's not going to make a difference as long as your calculations are made easy. Now, for time, we will assume that we have some kind of stopwatch or a clock that measures time. And just like for space, we have a number line. We are going to assume that for time also we have some number line, right? So time is a continuous quantity, just like length or position is a continuous quantity, right? This length is in general going to be a real number. Time is also a continuous quantity, so we can quantify it using a real number. So the time is going to be measured using a stopwatch, um, with t equal to 0. I can't show a number line for time because it's happening in time, right? Not in space. But the origin of that number line would be, the number line that extends in the time dimension, marking the origin or the beginning, which is going to be typically the beginning of the experiment or whatever event we are interested in. Now, um, using modern technology, we can actually use a video camera, right? Not just a stopwatch. We can have a stopwatch inside a video camera. We click on play, sorry, or record, and then it starts recording the position of a particle over time. So as the particle moves, everything gets recorded by the video camera, and we get a time lapse, motion, if we were to play back that recording. But what we will assume is that um, um, that kind of recording may not always be available. Instead, we might have a sequence of pictures or snapshots or measurements um, at different points of time. So maybe when we started measuring um, the motion of a particle, in this case, a car that's traveling along a one-dimensional road. So at t equal to 0, maybe the car was at position 30. Okay, so we can write this down in a table. At t equal to 0, we measured the car to be at position 30 using some units, meters in this case, and time measured in seconds. Then 10 seconds later, we took another picture of the car and it was at position B, which along the real number line, actually, like I said, we are going to be dealing with point masses. This is not really a point mass that you're seeing. So let's just pretend that this vertical line separating the two windows is where the point mass is. So at time, 10 seconds later, the car is somewhere at position 51, 52, let's see, 52. Okay. And so we get 6 different snapshots. 10 seconds later, the car is at this position. 10 seconds later here, 10 seconds later here, 10 seconds later here. So we can get a time-lapse photography, or we can get this kind of pictorial diagram, right? Likewise, if something is moving in the vertical dimension, maybe we have a cliff here. We can track how a point mass moves. Maybe time-lapse photography would show something like that, or rather a series of snapshots that are equally spaced might show something like that. So these are called motion diagrams, right? Motion diagrams. But these are not mathematical enough for us, because they are more complicated and descriptive. The way we would so what's varying in motion diagrams is, time is varying, and the position of the particle is also uh, varying. So we can represent our measurements as a table. This is this is called a tabular representation. So that's better because at least our data is in a table. But an even better representation is going to be a geometrical representation. And this is what we are going to rely on for our visual understanding of motion. Geometrical representation as a graph. So what we will do is we will take these two axes, one for the position axis and one for the time axis, and imagine having them perpendicular to one another. So lay down the time axis in one direction, the position axis in the other direction. And if a particular particle, so this particle was at positions 30 at time 0, we mark it at position 30 at time 0. So along the time axis, we are at t equal to 0, and along the position axis, we are at position 30. Then 10 seconds later, we know it's the particle was at position 52. So we have another dot here corresponding to x equal to 52 and at t equal to 10. Now I'm assuming that you're familiar with this from your 9th and 10th grade math. Don't worry about all these all the extra information here for now. Imagine that what we have are 6 points here. Don't even look at the curve connecting them. Just imagine that we have these 6 measurements, A, B, C, D, E, F, plotted along two perpendicular number lines, a space created by two perpendicular number lines, two-dimensional space. And this was the uh, representation that uh, you might have studied in 9th and 10th grade when you study the graphs of functions. So since the position varies with time, we can think of this graph as showing the relationship of how position changes with time. Now, what would uh, the graph look like if the particle had not changed its position at all? If it was a stationary car, what would the graph have looked like? Well, if the position had not changed with time at all, then whatever position it was in at t equal to 0, in this case it's 40, the particle would have continued being at that position across time, right? Um and this is being shown as a continuous line, assuming that you have a video camera that's recording those measurements continuously rather than spaced apart with a gap of 10 seconds. So a horizontal line makes sense. So this, we're going to call this as specifically the XT graph. Okay, this is the XT graph. Or we can say the YT graph. If we were depicting vertical motion, we would call it the YT graph. Essentially position versus time graph. position versus time graph. And when the position versus time graph is horizontal, it means the particle is at a fixed position. It's not moving. Does it make any sense for the uh, position time graph to be vertical? Can we have a position time graph that is vertical? Actually, that doesn't make any sense because uh, at a particular time, this is like saying at a particular time point, the particle was simultaneously at all of these positions. Makes no sense whatsoever. It's illogical. That is why in mathematics, when you study functions, you might remember uh, they have to pass what is called the vertical line test. So if you draw a vertical line anywhere here, it must cut the, this blue line or curve in general at most one point. It should be exactly one point in general where any vertical line should cut it. So it won't make any sense to talk about a position time graph where the position changes like this. This also doesn't make any sense because if I take a vertical line here, that means at the same time the particle was at three different positions. All right, so that doesn't make any sense. Um, our position time graphs have to um, satisfy the vertical line test. Now consider the example of Aristotle, Aristotle's physics. In Aristotle's physics, you have natural motion being vertical motion. So let's say a rock is dropped from the top of a cliff and it falls down. So we can represent this motion along the y-axis like this. Maybe we pick this point as the origin, and then this is 1, this is 2, this is 3, and so on. Or we could do something else. Maybe we have a y-axis like this, where this is position 0, this is 1, this is 2, this is 3, and so on. So either of them is fine. So uh, what would the YT graph look like according to Aristotle's physics? So when a rock or let's say a point mass is dropped from a height, and let's say it is at position 0 at t equal to 0. So at t equal to 0, it gets dropped. So so that means the particle starts out at y equal to 0 at time t equal to 0. So it starts out in the YT graph at the origin where the two number lines intersect. How is the YT graph going to look like for subsequent time uh, instants? So by the way, each uh, value along the time axis is called a time instant. Okay, each value along the time axis is called a time instant. It is a particular moment in time, which again can be represented as a real number. Just like position. So position and time instants are real numbers. And those are what we are plotting in the xt graph or yt graph. So at future time instants, where would the particle be located and what would be the pattern that we would see um, as we observe the motion?
Guys, you have to respond. Please respond in chat. Otherwise, it becomes a one-way exercise. You were asking, when are we going to solve problems? Here is your first problem. PC. Now we take away your right of being silent, PC. बताइए. Please tell us. Omkar sir has asked the first question of the class. Please respond. How will this graph look like? Someone is raising the hand. Let's bring in PC. Omkar, should I bring him in?
Yeah, I just unmuted.
Okay. PC, batao. Please tell. What will happen? बोलो अनम्यूट करके बोलो अपने आप को.
I think they might be pressing their raising their hands by mistake, Kapil. I think maybe, on the keyboard by mistake something happens and
Someone is saying parabolic, someone is saying straight line. किस basis पे बोल रहे हैं? I'm not able to understand. Uniform straight line. Can someone raise hand and explain the logic of it? Akshada, would you want to explain the logic of how you arrived at this? बताना चाहेंगी? Can we unmute you and you can join us? सीधा फेंकना नहीं है guys. मतलब there has to be logic to it. आकाश चौरसिया बताना चाहते हैं तो let us allow to talk. आकाश आ जाओ. आकाश बोलो. Unmute yourself. आकाश अपने आप को unmute करो. बोलो.
नमस्ते सर.
yeah, namaste.
Sir, because there is uniform acceleration.
आकाश हिंदी
So-
में बोलो, कोई प्रॉब्लम नहीं है. आकाश आराम से हिंदी में बोलो, कोई प्रॉब्लम नहीं है.
सर जैसे वो डिस्टेंस है सर, टाइम चेंज हो रहा है तो उसका जो रेट है उसको वेलोसिटी बोलते हैं.
Okay.
और
Okay.
वेलोसिटी का जो रेट है उसको एक्सीलरेशन.
All right. So, you have tried to answer the question based on how it will actually fall. I guess my question was, how will it fall according to the physics of Aristotle? How should this particle fall according to the physics of Aristotle? Which I don't know if you attended the earlier classes, but which essentially says that when you drop an object made of earth or water, it falls down at a speed that is proportional to the amount of earth or water in it. In other words, proportional to the mass. So let me actually quote. This is what people believed. A given mass moves a given distance in a given time. A mass that's heavier moves the same distance in less time, and the time being inversely proportional to the weight or mass. For example, if one mass is twice of another, it will take half as long over a given distance. This is the claim that was disproved by the alleged experiment from the top of the Leaning Tower of Pisa. But if this prediction is true, that any mass that you drop always moves the same distance in any time interval, that means after t equal to 1 second, let's say it moved here. Let's say it moved here. Whatever this position is, we don't know. But after one more second, it would have fallen by exactly the same amount. And after one more second, it would have fallen by exactly the same amount. And so the graph that you get, according to Aristotle's physics, for y versus t would be a straight line like that, which is what is shown here. Right? In your NCERT book, this is actually x versus t. I'm saying this is the graph you get for y versus t, where the position gets incremented by the same amount each time. Now, if you had a heavier mass, according to Aristotle, the curve would, the graph would look like that. It would fall at a faster rate. If you had a lighter mass, it would look like that. But everything falls at the same speed. Any object that's dropped falls at the same speed. So, uh, so that's one belief, and if you imagine each of these lines like a mountain slope, the slope of a mountain, uh, how do you define the slope? Well, you must have learned this in mathematics. The slope is essentially how much you rise when you run across by, let's say, 1 unit. So let's say I take one step to the right. By how much do I need to rise up to come back on that slope or to be on that slope? That ratio of rise to run is the slope of this line, and lines have a constant slope, right? You measure the slope um, anywhere along the line, it's always going to be the same. So the slope of the YT graph, the slope mm, the slope of the XT or YT graph is what we are going to define as the velocity of the particle. So whenever you see the word velocity, the definition is it's the slope of the XT or YT graph. And for now, at least, these graphs are simple enough that they have the same slope. Doesn't matter where you measure. Now, Aristotle also thought that uh, the slope or the speed or the velocity, right now I'm just using them interchangeably, uh, it's more for heavier objects. But for the same object, it can be more or less depending on what the object is falling through. So if it's falling through air, then the velocity may be more. If it's falling through water, then uh, the slope might look like that, because a rock sinks at a slower rate through water than the rate at which it falls through air. And so he was imagining that this velocity is going to be proportional to, firstly, the mass, and inversely proportional to, let's say, the resistance offered by the medium through which the object is falling. Right? So larger masses have more velocity as they fall, and denser mediums would have more resistance, which means the velocity would be smaller. Now, what happens if you make this resistance completely zero? If this is how velocity behaves for a falling object, then when you make the resistance or resistivity zero, then the velocity should become infinite. So if there was vacuum in space, there would be no resistance at all to motion, and that would make the speed with which something falls infinite. And that is a logical contradiction. Why? Because if you have an infinite speed, then our position time graph becomes like this. The particle is at multiple positions at the same time because it takes zero time to go from one position to another. And that was considered a logical impossibility for a particle to be at two different locations at the same time, which is why people did not believe that there could be anything like vacuum. If you accept this kind of physics, then you will say that vacuum is impossible to exist. Somebody had asked that question last time, so this might give you a better explanation for why Aristotle did not think, or why people in general oppose the existence of vacuum. Now, if this graph had been drawn using a different axis, like for example, this particular axis, then it would have looked different, because then um, we would have had the position being h at time t equal to 0. and then the object would have fallen by a certain amount every second, and the YT graph would have had a negative slope. So, and that's fine, right? So what you measure the velocity to be will also depend on the orientation of your axis. If you don't care about the orientation of the axis, you could only look at the magnitude of the velocity. So in this case, notice that the rise over run would be negative because there is actually no rise, there is a drop. So the rise is negative, but the ratio of rise to run would be the same in magnitude. And so the magnitude of velocity is what we can define as speed, where we don't care about the direction. But with velocity, we have a plus or minus sign that's indicating whether the particle is moving towards the plus x or plus y axis or minus x or minus y axis. Now back to this curve. Oh, sorry, back to this graph. If all we knew was that the particle is at these 6 locations at 6 different points of time, and we knew nothing about how it moved in between, this brown curve has just been made as a possibility. We don't know. We may not have the data that shows where the particle exactly was in between. Let's say we didn't have that at all. Then one simple way in which we could have imagined the particle going from this position to that position over 10 seconds is at a uniform velocity. That means at the same velocity, the same rate at which the particle would travel all the way. And that's shown by this blue line. So this blue line is something we would then call not as the actual velocity because we don't know how it actually moved. We just know the endpoint. We just know the two endpoints. So we would call this the slope of this line as average velocity. So the average velocity is something that we define assuming that we have constant rate motion between the two endpoints. So we have some endpoints in mind. All right, we have some endpoints in mind. And so the time between those endpoints is called the time interval. All right, so in this case, uh, the rise is going to be the amount by which the position changed, and the run is going to be the difference between the two time instants, which is called the time interval, and it's denoted as delta t, which is just another way of saying it's the difference between the final time instant and the initial time instant. So the word delta just means change. So whenever you see delta t, it's always changed in t. That means final minus initial, t final minus t initial. If we ask what's the change in the position, so in the xt graph, we would call it delta x. So change in position, which would be delta x, okay, which would be x final minus x initial. So I wrote average motion here. What I meant is average velocity. So average velocity is defined. It's defined like this. I'll just write it like this. Average velocity is defined to be delta x by delta t. This is the definition. Pretend that the motion is happening at the same rate. What rate would that be? That would be the average velocity. So the numerator in particular, this delta x quantity, change in position, that's also given a name. So the denominator delta t is given a name. It's called the time interval. The numerator, which is the change in position, is given a name. It's called the displacement. So think of it as just an arrow that goes from the initial position to the final position, and you're asking what's the length of that arrow. But if the arrow, if the position had changed in the opposite direction, so if we look at the motion from B to C, then the change in position would have been a smaller number minus a bigger number. So it would have been negative, indicating that the position changed towards the negative direction instead of towards the positive direction. So now that we have a coordinate system, we know what direction is positive, what direction is negative. That's imposed by the coordinate system. And so the change in position, the sign of the change in position, the sign of the displacement would give you the direction in which the position changed. And the magnitude would give you the amount by which it changed. Now, in reality, uh, knowing the displacement does not tell us what happened inside the time interval, right? Like here, we don't know what happened in between these two time instants. We know that overall the displacement is this, but the particle could have moved like that, or it could have moved along this brown curve, or it could have gone like that. The displacement does not capture that information. And this is seen in a simple example. In a football field, if a player runs from one end to the other and then comes back, the change in position or the displacement is 0. And it would have been 0 even if the player had just been stationary there. So both scenarios would result in 0 displacement. So, but the player did move, right? We know that the player followed this particular path if we recorded everything with a video camera. So, because the displacement is 0, if we ask what is the average velocity of the player starting from the moment when the player started running in that direction and ending when the player came back, since the displacement is 0 and since the average velocity is defined as the ratio of the displacement to the time interval, delta x by delta x is 0, so average velocity would be 0. So the xt graph in this case would look like what? Maybe the player started here. Let's call this as x equal to 0, and this is some maximum value. So the player would have run from 0 to that maximum value and then come back. This is one way in which the motion could have happened. But we know the distance the player traveled. We know that the player did go along a particular path, and the total length of this path is called the distance. So the length of this path is called the distance. So the distance is different from displacement. The distance can never be negative because it's just the raw length of the path. The displacement can be negative if the if net there was a motion towards the right. It can if it would be positive if the particle changed its position to go towards the right. But if the change in position happened towards the left, then the displacement could be negative. But the distance would always be positive. So if we look at this question, uh, showing, so think of this as the xt graph. Even though they call it ST. So the xt graphs of two moving particles A and B is shown. What is the ratio of their respective velocities? Okay, some people are saying, can I infer that negative sign for displacement means the object moves towards the initial point? Not necessarily. Not necessarily, because suppose a particle started at the origin and the particle started moving towards the left, right? So in that case, the final position, the change in position would be, negative, because if this is x final and the origin was x initial, then x final is a negative number, x initial is 0. So the displacement would be negative, even though the particle is not moving towards the origin, it's moving away from the origin. If it was on the right side of the origin, then it could be moving towards the origin. But the sign of the displacement does not tell you whether or not the particle is moving towards the origin, because it could be either. All right, most people are saying 1. There's just, I think, a couple of answers that are different. Um, so so this is where, you have to fall back on the definitions of these quantities. Firstly, if this is the position time graph, so let me first write this down. In an xt graph, if x was 0 at t equal to 0, then the position at any time would be the same as the displacement. If I'm starting at x equal to 0 at t equal to 0, then at any future time instant, if I am at any particular position, that's also going to be my displacement, because x final minus x initial would just be x final minus 0, which would just be x final. So the position and displacement would be the same. So whenever you get a graph that says displacement time graph, you can assume that it is a position time graph. It's just that the position is being assumed to be 0 at time equal to 0. All right, so this is really the xt graph. So that's one clarification. So the displacement time graph is essentially the position time graph with initial position 0. Now, particle A is moving towards the right? The position is increasing as a function of time, and this straight line indicates that the rate at which it's changing its position is fixed, like a mountain slope, like a mountain slope with the same gradient everywhere. So what would be the velocity of this particle? The velocity of this particle A, by definition, what is the velocity? The velocity is just, going back, what did we write? Mm. So the velocity was just the slope of the xt graph, right? Which can be written algebraically like this: rise over run. It's just the slope of the xt graph, which can be written as rise over run. Now, in your geometry, you might remember that one way to get the slope is to take, so we have to take the ratio of rise to run for any triangle. You draw any triangle along the slope, measure rise, measure run. That ratio should be the velocity of A. But here we have a right angle triangle, and we are talking about the ratio of the altitude or the perpendicular to the base. Now, again, going back to your probably 9th or 10th grade geometry, the ratio of the perpendicular to the base in a right angle triangle is defined as the the tangent of that angle. Since this angle is given to be 30 degrees, we don't need the coordinates of these points because all right angle triangles with a base angle of 30 degrees have the same rise over run ratio. So that would just be tan 30 degrees. So the velocity of particle A would be tan 30 degrees. I'm not mentioning the units here. But because it's the ratio, in the numerator we have change in position, so the units would be the units of length, and the denominator is the ratio of is the difference between two time instants. So there the unit would be the unit of time. The unit of the slope here is going to be length over time, meters per second if length is being measured in meters and time in seconds. So tan 30 is something you should be memorizing. You should know the ratios of, you should know the sine, cosine, tangent values for angles, common angles like 30 degrees, 45 degrees, 60 degrees, 90 degrees. Um, Even the special 3, 4, 5 Pythagorean triplet, right? The simplest right angle triangle satisfying Pythagoras' theorem, 3 square plus 4 square is equal to 5 square. This base angle is 37 degrees. This is 53 degrees. You should memorize that whenever you have a base angle of 37 degrees, we are talking about a 3, 4, 5 right angle triangle with 3 as the altitude and 4 as the base. So for some common angles like that, you should know the sine, cosine, and tan ratios. In the same way, the velocity of B would be tan of 45 degrees. So tan of 45 means it's a triangle, a right angle triangle, where this angle is 45 degrees. So that means this angle is also 45 degrees because the sum of the three angles have to add up to 180. So it's an isosceles triangle. If this length is h, the base will also be h. So tan 45 is 1. So that means the ratio VA to VB is going to be 1 over square root of 3 divided by 1. So 1 is to square root of 3. This is the correct choice. Any questions on this? Yeah, some of you got option 1. And like I said, for most answers, oh, okay. Most people said 1, probably you meant option 1 and not the answer 1. So I might have misunderstood. Okay, so looks like it is a relatively easy problem for at least most of the people who are responding. So that helps me in adjusting my pace. All right, let's look at a particle that's undergoing motion according to the following xt graph. The question is, what is the distance traveled by the particle from t equal to 0 to t equal to 6? Recalling the difference between distance and displacement. Let's also find the displacement. So the displacement would just be the final position minus the initial position. X final, we write this as delta x. X final minus x initial. So x final is how much? At t equal to 6, the particle is here. So that's 2. At t equal to 0, the particle was at 2. So the displacement is 0. But like the football, the player who ran from one end to the other and came back, in this case, the particle went from x equal to 2 to x equal to 0. So the particle moved by 2 units in the first 3 seconds and then moved back by 3 more units. Sorry, by 2 units and then moved back by 2 more units from t equal to 3 to t equal to 6. So this motion was 2 meters. This distance was 2 meters. This distance was 2 meters. So overall, the distance would be 2 plus 2. Right, 2 meters plus 2 meters. So that's 4 meters. All right. Um, before I look at this, actually, you can solve this even now based on what we've done. So a person who walks for exercise produces the position time graph shown here through a health app or whatever, something that they're wearing. Without doing any calculations, decide whether the segments A, B, C, or D indicate positive, negative, or zero average velocities. So when you look at segment A, you're looking at what happened from this endpoint to that endpoint. When you look at segment B, you're looking at what happened from this endpoint to that endpoint. So without doing any calculations, can you predict, is the average velocity going to be positive, negative, or zero here? Well, the slope here is increasing. I mean, it's positive. The height here is increasing, not the slope. The height is increasing here. And so the rise over run ratio is going to be positive. So positive here. Here it's falling. So the average velocity is going to be negative. Here it's again rising. So the average velocity will be positive. And here it's flat. That means the position didn't change. So the average velocity will be zero because the displacement will be zero. Now, what if we had to calculate the average velocity for each segment? So I'll do that quickly here. The average velocity in segment A would be delta x by delta t. Fall back on the definition of average velocity. That's 1.25 minus 0 divided by delta t would be 0.2 final minus initial. And it's in kilometers per hour. Okay, whatever that value is. Average velocity over segment B would be final minus initial. So 0.5 minus 1.25 divided by 0.4 minus 0.2, again kilometers per hour. At C, it would be delta x, so final minus initial, 0.75 minus 0.5 divided by 0.8 minus 0.4, again in kilometers per hour. And finally here, we know that this is going to be 0 because the final and the initial positions are the same. But this would be the expression if you were to do the calculations, and this would end up being 0. All right. So Even though the displacement and distance are not the same, as we've seen, sometimes they can coincide. So just like we have the average velocity be the total displacement, x final minus x initial divided by the time interval, or I can just say total time elapsed. We know from the example of that football player that even if this is 0, the player might have traveled a certain distance over that time interval, as we also saw in this particular problem. So what if we found the total distance and divided that by the total time elapsed? That would indicate, on average, how fast was the player moving, irrespective of which direction the player was moving in. This is called the average speed. So the average speed is going to be defined like that. Now, one of the reasons why, so at this stage, it's often hard to appreciate why are speed and velocity, why are we making such a hue and cry about the difference between speed and velocity? The significance actually comes later when you look at topics like collisions. Just to give you an idea, Descartes, who you might have heard about as the founder of the Cartesian coordinate system, which is actually named after his last name, Descartes Cartesian. He was the one who actually came up with a way to unify algebra and geometry by showing geometrical figures on a coordinate system so that these figures could not only be drawn as they used to be earlier in geometry, but you could come up with equations for the lines or curves making up the figure, algebraic equations using symbols. So instead of uh, analyzing geometrical figures by thinking about their shapes and doing the proofs that you might have learned in high school geometry, you could manipulate them using algebraic symbols and derive properties just by doing algebra. That was the advantage of the Cartesian coordinate system, that it helped to unify algebra and geometry. Now, Descartes was also trying to build his own physics, like Galileo and Newton. He actually knew he came to know about Galileo's trial and that Galileo was put under house arrest. But Descartes was living further north, I think in Holland or somewhere where he was not under threat. But he used to have some illness which made him get up very late in the mornings. He used to just lie on the bed looking up at the ceiling. And one day when he saw a fly move on the ceiling, um, ne pretty close to the junction near the, where the three walls, where the ceiling meets um, the two perpendicular walls. And looking at how the fly moved gave him this idea that if he could have three axes corresponding to the three, you know, uh, boundaries between the two walls, one of the walls in the ceiling and the other wall in the ceiling, the junction which might look something like that between the three walls. If we could have treat them as independent axes, then the fly could be given an address in that 3D space, and then how it moved itself could be analyzed by looking at how those three numbers changed over time. And so working on that, he developed this coordinate system and the math, the unification of algebra and geometry in that coordinate system. But one of his beliefs was that when God created the universe, uh, he must have set it going in a way that does not require his continual interference, right? Like when somebody creates a clock, when a clock designer creates a clock, the clock continues to operate on its own without the designer having to, always manually keep rotating the hands of the clock and so on. That's not a sign of good design if you have to keep interfering in what you designed. Uh, so there must be something conserved in the universe which keeps it going, which does not require God's continual involvement. What is that quantity which God set up at the beginning, which keeps the universe going? And so he was searching for some kind of, you can say, conservation law. And what he claimed is that the total amount of motion in the universe is conserved. The total quantity of motion in the universe is conserved. So even though some particles might slow down, others might start moving faster. If motion was not conserved, then the universe would come to a grinding halt, like a clock might come to a halt and again require some human to set it up, set things up going. So the thing is, how do we define the quantity of motion, the total quantity of motion in the universe? If the universe is made up of these small particles, if we can define the amount of motion contained in one particle, we could add up the total amount of, we could get the total amount of motion in the universe by adding up the amount of motion in each particle. So what indicates the amount of motion in each particle? Well, one quantity is certainly how fast that particle is moving. So that's called speed. Okay, let's work with speed, not making a distinction between speed and velocity for now. So speed, the more the speed, the more the quantity of motion in a particle. Another thing that the particle has is mass, right? So more the mass of a moving particle, more the quantity of motion in it. So a truck traveling at 20 kilometers per hour has more motion than a ball that is rolling at that same speed, right? Because they are just two completely different masses.
Omkar,
So
I
he
want
thought
to
that,
interrupt.
yeah,
Can I quickly interrupt
yeah.
for a minute? Omkar, what is happening is, help me understand. Are you building constructs of a lot of things based on which we are going to do the analysis of things around us?
Uh, Sorry, didn't get your question. What's the,
I'm saying, for example, when you say conservation of motion, right?
hmm,
You are defining stuff, right?
yeah,
Mass, speed. It will lead to at some point of time momentum, which these kids will also know. So what
hmm.
I was saying was, is physics understanding a lot of definitions and then applying them in problem solving, or just uh, observing the nature around you? And should we give these students bullet points in terms of these are important constructs which you should understand?
Yeah, so right now this is just an attempt to explain why should there be a separate definition for speed and velocity. It looks very artificial when you're just doing kinematics, right? Is there any deeper motivation for making a distinction between speed and velocity? Uh, because otherwise you do see that velocity is defined using a mathematical ratio. Displacement is defined like that. So, like I said, this chapter is mainly mathematical because it's about understanding from graphs what slopes are and giving those slopes a name. The slope of xt graph is called velocity. The slope of velocity time graph, which we are not looking at today, but that would be given a separate name. You could give a separate name to the slope of acceleration time graph. You could call it jerk. You could give a separate name to the slope of the jerk time. So there's no end to how many names you can come up with. So ultimately, whatever we are defining has to have some significance in nature. Otherwise, we can just keep, defining slopes of slopes and slopes of slopes and keep going forever. So why is it that the quantities that we have selected are the only quantities that are relevant? And why is each of them relevant? That would be a natural question, right? So for motion, it's very clear that change in position matters because that's what motion is. The rate at which that position changed is something we perceive because some things move fast, other things move slow. So it makes sense to quantify that as well. These are the only two things that makes sense to quantify right now for kinematics. But even in talking about how fast something is moving, we are making a distinction between speed and velocity. So I'm trying to explain, is there anything deeper behind that distinction? Why not just deal with speed or just velocity? Why do we need both of them? Does that make sense?
It does to me. It does to me. Students can also quickly answer whether it makes sense to them, and then we move forward. Guys, please understand.
Now,
A lot of
yeah,
you,
and
sorry.
I think it's important to understand that these quantities are all human defined. That is the thrust of, all my classes here. There is no God-given definition for velocity or acceleration, these quantities just don't exist in nature. These are quantities that we define because there is something we are trying to solve or understand, for which defining that quantity makes sense, or which where it's useful to define the quantity. It has to serve some purpose. Otherwise, there are a zillion things you can define with no end.
No, I mean, it is also helping Omkar for people to talk to each other. When I
Mm.
say acceleration, you would understand what acceleration is. I don't have to give a very, very long definition, right?
Yeah,
It is a common thing.
yeah, yeah. So this idea of conservation of motion, there is no proof for it. This was just a conviction that Descartes had, that the total amount of motion must be conserved. Only then can there be activity in the universe that continues with no end without God having to repeatedly inject motion, uh, like an imperfect clock designer who has to keep, manipulating the hands of the clock from outside. So it makes intuitive sense. Now, it makes intuitive sense to define the quantity of motion in any particle as proportional to its speed and proportional to its mass. Um, and so mass times speed can be the quantity of motion. And this is a human definition, right? I'm just trying to say that it's not illogical to define the quantity of motion in a particle like this. So the total quantity of motion in the universe would then be what? Would then be the summation of all the uh, masses and the speeds. Maybe I'll just use uh, VI, but think of these as speed. Not We don't have anything like velocity, right, in this notion across all the particles. Okay, so the sum of the product of the masses and speeds of all the particles must be conserved. This is what Descartes thought made sense. Now, people then started testing this view by having by analyzing collisions. So consider what happens when two equal masses, and these were experiments that were done by Robert Hooke, Christian Huygens, and others. If you have two masses that are approaching each other with the same speed, okay, they collide and then they just come to rest. All the motion is wiped out. According to Descartes, the total quantity of motion here uh, would be what? mv plus mv. That's 2 mv before collision. And what is the amount of motion here after collision? It's zero because they start moving. So where did that motion go? Um, for Robert Hooke and Huygens, this quantity was not very satisfying. But Huygens realized that there is a way to, you know, try to come up with a tweak of this formula so that the quantity of motion can be conserved. If we can have a coordinate system where this direction has a positive sign and this direction gets a negative sign, then the quantity of motion in this can be called as mv, but the quantity of motion in this would have to be called as m times minus v because the speed is in the other direction. So in that case, the quantity of motion before collision is also zero and after collision is also zero. So this is a way in which we can preserve this notion that the total quantity of motion in the universe is conserved uh, without and being able to handle what happens when different particles collide. So that is where instead of speed, a quantity which is numerically equal to the speed, but for which we are also mindful of the direction, had to be defined, and that's called velocity. All right, so the reason why velocity is going to be important is because this is going to come up in the, down the line. Today, we would call this quantity of motion as momentum. And velocity is something that would have a sign, right? Would have the direction is something we have to keep in mind. So, so in the one-dimensional case, therefore, I said, and this is a one-dimensional collision, right? So even in a one-dimensional context, you can see that if you bring in these theological beliefs from outside, then you understand the motivation behind the definition of these quantities better. Otherwise, it's just, a bunch of dry definitions with no purpose. There was purpose here. The purpose was to describe the universe in a way, or to understand the universe in a way that is consistent with the religious worldview that people had during that time. Okay, somebody said not getting, sir. Uh, um,
Should I bring in Sadia, Omkar,
sure.
or
Yeah.
okay. Sadia, can I unmute you and can you tell us what you did not understand? आप हमें बता सकते हैं क्या समझ में नहीं आया? We have a small nice group. यदि आपको नहीं समझ में आ रहा तो we can quickly go over it. Allowed to talk. सादिया बोलिए क्या समझ नहीं आया? आप हिंदी में बोल सकते हैं, कंफर्टेबल है उसमें, हिंदी में भी बोल सकते हैं. That is not a problem.
जस्ट वही वेलोसिटी और स्पीड का मेरे को अभी तक क्लिक नहीं हो रहा है वो जो सर बताना चाह रहे. समझ रहे हैं कि M1 V1 प्लस M2 V2 वो समझ रहे हैं, लेकिन फिर वेलोसिटी का फिर वो चेंज हो जा रहा है ना. वेलोसिटी इक्वल टू डिस्प्लेसमेंट, राइट?
Velocity is equal to change in displacement over change in time. तो अब वो वैसे क्यों डिफाइन किया है? Why did people define it like that? Um, because defining it like that means that when the particle is moving to the right, the velocity would be positive. When the particle is moving to the left, the velocity would be negative, according to our convention for the number line. But why did people want to define velocity like that? Why couldn't we just consider the magnitude of the slope to be the velocity and just not have two separate quantities, speed and velocity? Why why make a distinction here between speed and velocity? So उसके लिए मैंने motivation बताया कि the intent, there was a belief that the total quantity of motion is conserved. This was a conviction Descartes had, and he came up with this view that mass times speed को अगर आप multiply करो हर particle के लिए universe में, तो वो total conserved होना चाहिए. Then only the motion in the universe will continue in a self-contained way without requiring external interference. But ये वाला जो collision का example है, this disproves the claim that motion is conserved because इसमें collision के पहले total quantity of motion क्या था? mv plus mv, that's 2mv. After collision 0 हो गया, so the total quantity of motion in the universe got decreased by 2mv. So there is no conservation then. But Huygens felt that we can change this. Instead of calling the total quantity of motion in the universe like this, where what we have here is speed. Speed is always positive, right? Non-negative. Why not give directionality also importance? Because if we give directionality importance, then these two motions are canceling each other out even before collisions, because one of them is towards the right, the other is towards the left. And so the net motion, if we add the two motions keeping their directions in mind, we would actually be subtracting them instead of adding them. So that is why velocity had to be defined as a vector. What is a vector? A vector is just giving some physical quantity uh, a direction also, being mindful about what direction it is in. So giving that importance can help preserve some kind of conservation law in the universe. And that is what we would call as conservation of momentum today, linear momentum. But अब ठीक है, now it's fine.
सादिया बताइए, नहीं समझ
I
आया?
think she said yes. She said
Oh,
yes.
she said yes. Good. Okay.
Okay.
तो सादिया मैं
So
आपको कर रहा हूँ अभी, है ना? If you have any problem, आप वापस पूछ सकते हैं, लिख दीजिएगा वहाँ पे. I am here to help ओमकार सर.
so so actually that is why speed does not have as much importance in physics as velocity, because velocity seems to have this deeper significance that there is something conserved about the total amount of motion when you look at these collisions. And so that's why at some point, we stop giving importance to speed. But having said that, there are some problems that you should be able to solve for average speeds as well. So just like I said, average velocity is defined as the total displacement over the total time. The average speed would be is something we can define as the total distance over the total time. ये आपने elementary school में सीखा होगा. Speed is distance over time, right? For uniform motion, for motion that's happening at the same speed, we can assume this. But even if it's not happening at the same speed, if all we know is what the total distance traveled is and what the total time was, if we had to characterize that motion by a single number, we can assume that everything happened, at a uniform rate, rather than sometimes going faster, sometimes going slower. Neglect all that. On the whole, what happened was this much distance was traveled in this much time. So we can define a quantity called average speed based on that. So let's tackle a couple of questions on average speed. Let's do part B first. Please attempt part B first before part A. So you go on a bike ride and you ride for half the time at 10 miles per hour and half the time at 20 miles per hour. What is your average speed? $15. Okay, most people are saying 15. Um, yeah, so how do you get 15 from the definition of average speed? So average speed is the total distance over the total time. Uh, so um, so let's say the total time. So when we are not given the total distance and we're also not given the total time, right? So what can we put here? The algebraic approach is when you're not given anything, just assume some variable. So let's say we assume a variable t for the total time. All right. So this means now translate all the information that's given in the problem into claims or equations in terms of this variable. So for half the time we rode at 10 miles per hour, right? So for t by 2 seconds or hours maybe, for t by 2 time, I'll just say t by 2 time, speed was 10 miles per hour. And for the remaining t by 2 time, the speed was 20 miles per hour. So can we express the total distance and the total time in terms of this variable t? I just use one variable. Ideally, you should not try to use more than one variable to start with. So everything has to be translated in terms of that one variable. So total time, of course, is what we assume to be t. Can the total distance be expressed in terms of that variable, whatever information we have? Well, if for t by 2 time the speed was 10 miles per hour, then the distance during this first half would have been speed times time, right? So 10 times t by 2. And in the other half, the distance that was traveled was 20 times t by 2. So 20 times t by 2. And now everything is expressed in terms of t, and indeed we see cancellations happening here. The t in the numerator cancels with the t in the denominator. And we get 10 by 2 plus 20 by 2. So that's 30 by 2 or 15 miles per hour would be the average speed. So the average speed ends up being intermediate between 10 and 20, exactly the middle of 10 and 20, 15. But be careful when you find the average by just taking the average of the two extreme numbers, because that might not always work. Let's now get to part A. Try part A. You ride a bike uphill at 10 miles per hour and then down back the hill at 20 miles per hour. What's your average speed? $13.3. Okay. 40 by 3. All right, so I'm not getting many responses here, probably because people are finding this part A to be harder, which it is. It's more tricky. So let's think about it. How do we start this? One way to start this is to do the same thing we did here for part B. Assume t to be the total time. The problem with doing that, there's a problem with doing that. Problem is that we don't know how time was divided up in the uphill portion and the downhill portion. In part B here, we knew how time was divided. It was half the time at this speed and half the time at that speed. But when going uphill and downhill, you'll be going slower. It'll take more time to go uphill and then less time to come downhill. And I don't know what the division is like. So taking time as a variable um, might not be a good idea or might not work here. So why not take the total distance as a variable? Because for the two halves, I know that the distance was the same. Whereas in part B, the distance was not the same for the two parts of the motion, right? The time was the same for the two parts. So it made sense to use time as the variable, which could be divided into two parts. For part A, the distance is the same in the two parts. So it makes sense to use distance as a variable. So that way we won't hopefully need more than one variable. So if I let d be the distance uphill or downhill, right, one way. So if the mountain was like this, the length of this path from here to here would be of length d. Now let's translate the information given into uh, statements or equations in terms of that variable. You ride a bike uphill at 10 miles per hour and then down the hill at 20 miles per hour. What is your average speed? So Again, we don't have to intuitively think. Fall back on the definition of average speed. How is average speed defined? It's the total distance divided by the total time. Can we translate both of these, the numerator and the denominator, in terms of the variable d? Well, numerator is pretty obvious too. It was d uphill, d downhill, so the total distance is 2d. Can we translate the total time in terms of the variable d? Well, the total time would have been the time to go uphill plus the time to come downhill. How much time would it take to go uphill if I'm going at a certain given speed? So let's see, time would just be distance divided by the speed. So d by 10 would be the time it would take to go uphill, and d by 20 would be the time it would take to come downhill. So the total time would just be, therefore, d by 10 plus d by 20. And now the d's cancel out, and I get the sum of 1 by 20 and 1 by 10. So that's just sum of 2 by 20 and 1 by 20. That's 3 by 20. So this is just, so 2 divided by a fraction is just 2 multiplied by the reciprocal of that fraction. That's 40 by 3 miles. Okay, since the units were in miles per hour. So 40 by 3 is the right answer. And it's 13.3, of course. So yeah, that's tricky here, right? Because notice that the average speed ended up being 13.3, which is actually less than the midpoint. It's not the average of 10 and 20. The average of 10 and 20 was 15. And that made sense if, as long as you were going at 10 miles per hour for the same time as you were going 20 miles per hour. Then you can say the average speed was 15. But if you're going the same distance for 10 miles per hour and for 20 miles per hour, then you're actually spending more time going at 10 miles per hour and less time going at 20 miles per hour. So overall, the amount of time you spend going at 10 miles per hour is more. So the average speed is going to be biased towards 10 miles per hour than towards 20 miles per hour. It won't be exactly in the middle. And you can see that 13.3 is closer to 10 than to 20. Right? So notice that we took different variables here. Why? Because based on what information we were given, uh, um, time made sense in part B, distance made sense in part A, because we could divide them up that way. If we had taken the other variable, we would not be able to work with a single variable. All right. Now, there's actually, if some of you think a little deeply, I explained why velocity and speed, why speed was not sufficient and people had to, think of a quantity called velocity. You might also ask, why is average velocity so important, right? Isn't the motion, what happened in between, quite important? How can we just say, for example, that I don't know what happened between A and B, so I'm just going to assume this is a straight line. I don't know what happened between A and E, so I'm just going to assume the motion in between was a straight line. Well, if you have no other information, that might make sense. But ideally, you want to know what happened throughout, right? Ideally, we want to know what happened throughout. And notice one unfortunate fact here, that if I had computed the average velocity, velocity is more important than speed, right? I explained why. If we had looked at average velocity from A to B, you would have got some positive number because this is going up. If we had computed the average velocity from A to E or A to F, we would have got a negative number because the slope is coming down. As we go to the right, we don't rise up, we fall down. So we get two completely different values. In fact, from A to C, it might have been slightly positive, but the numerical value we would have got for average velocity would be very different from A to B. So the question is, for when different time intervals are going to give you different values of average velocity. Why is this, like, what is so sacred about this quantity called average velocity? And the truth is that there is nothing sacred about it. Actually, it doesn't, what we care, what we ideally want is information about every single time instant from A to F, right? We want information about every single time instant from A to F. We want a complete video recording. And let's say we have a complete video recording. Let's assume that this brown curve is now giving you the position at every instant of time from t equal to 0 to t equal to 50. Now, why care about average velocity? Because the values are different anyway for different time intervals. There's no reason to think one. Well, actually, you can say that this value is a little better than that value. You know why? Because if the time interval is short or shorter, then it's likely that the any fluctuations in the velocity along the way, so think of going from here to there in a car, right? One possibility is that the car was going at the same speed from here to there. Another possibility is that sometimes it was speeding up, sometimes it was slowing down, and we got there. But if the time interval we look at is shorter, the fluctuations in the speed would have been less in general. So um, that means shorter time intervals are in a sense better because they hide less information. There's less leeway for information to be hidden if the time intervals are shorter. So, um, so what if we make the time interval even shorter? Because even between A and B, you can see that there is scope to deviate from the average, right? Because it need not have been at the same speed. Um, so what if we make the time interval even shorter, even shorter, even shorter? We would get something like this. So let's zoom into this region from A to B. We could do this for any time interval actually, but we're just taking this as a sample. Let's zoom into A to B. If the time interval was from here to there, sorry, from here to there, then the average velocity would have been this. If the time interval was a little shorter, right, I'm moving the point a little bit there, then the average velocity would have been that. If the time interval was even shorter, it would have been that. If it was even shorter, it would have been that. All of these lines, they are like chords in that curve, right? So we call them as secant lines. You might remember from your geometry that secants are lines that would cut a curve like a circle in two different places. And as we make the time intervals shorter and shorter, because we want less fluctuation from what's actually happening in that time interval, inside that time interval, we get secant lines that are getting closer and closer to this green line, which is the tangent line. So tangent is a line that cuts the curve at only one point instead of 2 points like secant lines, at least in that location that we are talking about. Um, so the secant line is approaching the tangent line, and if we imagine making this interval so short that it is infinitesimally small. So this is an idea that you need to grapple with, that make the time interval. That means, so let's say you're recording with a video camera, right? At t equal to 0, you saw what the position was. And then look at the position maybe in after t equal to 0.000001 second. For that tiny time interval, you would get a value for the average velocity, which is going to be, pretty close to which is going to describe the motion in that tiny time interval really well, because the fluctuations would be, almost nothing. So make the time interval so small, and instead of calling it delta t, so delta is the Greek letter for d, right? When you in the Greek alphabet, delta is what we would denote as capital D. So to indicate that it is a really tiny time interval, we'll call it as small t, right? It still means the same thing, t final minus t initial. It's just that the interval is very small. That fluctuations are not happening. That is, uh, within dt, within that interval, we can assume the velocity was constant. And if you find that no, it actually did vary, then make the time interval even smaller. If you find that, oh, it was still deviating, then make it even smaller. Make it as small as you like. So dt is called an infinitesimal. This is an infinitesimal quantity. Sometimes it's also called as a differential, a tiny difference, an infinitesimally small difference. So which number is it? So the thing to keep in mind is it's not zero. Okay. dt is some quantity that is greater than zero, but it is smaller than any number you can think of, than any positive real number you can think of. So it is a conceptual quantity. Is it smaller? If you ask me, is it smaller than 10 to the power minus 100? I'll say yes. Is it smaller than 10 to the power minus a million? I'll say yes. Is it zero? No. It's more than zero, but it's smaller than anything that you can come up with. Okay, so if you imagine an interval that is so small, then we can call the change in position. So change in position in that interval will also be a very small quantity. Let's call that as, instead of delta x, we'll call it as dx. Now, if we take the average velocity in that interval, that is going to be by definition delta x by delta t. All right. It's just that the interval is really small. So geometrically, the slope of the secant line is getting closer and closer and closer to the slope of the tangent line as we reduce the right endpoint, as we bring the right endpoint closer and closer to the left endpoint. Algebraically, dx by dt gets closer and closer to the slope of the tangent line. We will look at how this happens algebraically. For that, we need an algebraic definition of this curve to see what dx by dt will be. So we'll do that in a few minutes. But I'm just saying the average velocity in that interval, because this interval is so small, can be considered. By the way, dx is really small. It's an infinitesimal. dt is also an infinitesimally small quantity. Their ratio need not be small. Right? Dx is an infinitesimal, dt is an infinitesimal. But when you take the ratio of two really small quantities, it can be significantly large. In fact, that is the average velocity, right? And dx by dt in that tiny interval can be considered the velocity at that instant, instantaneous velocity at that time. All right. So if along the time axis we were looking at, let's say, time t and time t plus dt, and this was the position At time t, this was the position at time t plus delta t. Then we are saying that this rise over this run, this slope, is really the velocity at this particular time. In fact, that's how your speedometer reading comes. Basically, you look at the position. Essentially, this would be done through rotational motion, but think of it, if you were to do it through a video camera, you would make two measurements that are really close to one another. And if you can make out how much the position changed by, the ratio of that would be closer and closer to the speed at that time t. So the instantaneous velocity at that time. Actually, you might feel one way that, yeah, it doesn't make sense to talk about the velocity at an instant, because at an instant, what's happening? Nothing. Everything is frozen in an instant. You need a time interval to talk about motion. But what we have here is a time interval. It's just that it's so small that it's smaller than anything you can imagine. It is not a single time instant. It is an infinitesimally small time instant. So even though we talk about the velocity at that instant, we really mean the velocity in a tiny time interval around that instant, which is infinitesimally small. So we can therefore say that the instantaneous velocity is the ratio of the average velocity as delta t approaches 0. So the way we write this in mathematics is, now don't get scared by this notation, right? All that this means is delta t is getting closer and closer and closer to 0 when delta t is approaching 0. When we use the word limit, we mean it's getting close to 0, but it's never equal to 0. You never reach that limit. It's like a wall that I'm getting closer and closer to, but I never really touch it. I get closer to it than any number you can come up with. If you ask me, am I closer than 10 to the power minus 10 meters to it? I'll say yes. Am I closer than 10 to the power minus million meters? I'll say yes. Doesn't that mean I'm touching the wall? I'll say no. I'm still not there. Exactly. So this is just denoted as dx by dt, and this is called the instantaneous velocity. Um, so let's do a simple example using algebra. So geometrically, I hope you see what's happening. Geometrically, we are reducing the time interval, and the slope of the secant line approaches the slope of the tangent line. To see what happens algebraically, we need an algebraic representation of the position time graph first. So, so let's assume, this is just as a simple example of how we might calculate the instantaneous velocity. Assume that the position time graph, the xt graph, which looks like, let's say, this, all right, is described using with Descartes' help using an algebraic equation that is x is, let's say, equal to, I don't know, let's say t square for simplicity. So think of this as some kind of parabola, a simple parabola. X is equal to t squared describes the position, is the description of the position time graph. So this is the algebraic description. Okay, earlier we talked about pictorial descriptions, tabular descriptions, and so on. The important things, the two important representations are geometric in the form of this xt graph, and algebraic in the form of an algebra equation, which is essentially capturing the same information that's in the graph. You can, if I had this entire graph, I could come up with this equation. If I had this equation, I could draw this graph. Can go back and forth between them. It's like two parallel tracks, which really, or two different languages, a more visual language and a more symbolic language, which essentially say the same thing, which have the same information in them. The algebraic language is easier to work with because it is a finite equation. The geometric description is an infinite description, and it has an infinite number of points. The power of algebra is that it can take an infinite number of points that are arranged in a particular pattern and describe it using a succinct equation, which captures an infinite number of, uh, you know, points that if you were to describe one by one would take you forever because there's an infinite number of them. So let's say this is x is equal to t square, and now I take a particular uh, time instant. Let's say I'm just going to make it arbitrary, okay? Just so that it's not 3, it's not 4, it's not 0, it's not 1. It can be anything. We'll later on, once we have the result, I can replace t by whatever I want. But I want to measure the instantaneous velocity at time t. So what do? I'm going to take two time instants that are really close, and I'm going to measure the values of the position at those two time instants. So what is the slope? What is the average velocity in that time instant? Well, it's just going to be the x value at time t plus dt minus the x value at time t, that's the rise, divided by the t value, the t final minus t initial. So that's going to be what? What is the x value at time t plus dt if this is how the x value varies with time? I just have to replace t by this quantity, t plus dt. This is the time instant I'm worried about. And the square of that is going to give me the x value. So the x value at time t plus dt is just the square of t plus dt, and subtract the x value at time t, time capital T. So I'm just going to replace this little t with capital T. Divided by, in the denominator, the capital T's cancel out and I get this. Right, and it's understood as dt approaches 0. I could write this as a limit, but instead of using the scary notation, I can just assume it's understood when I'm writing it as dt. It's understood that I mean something infinitesimally small. So now I do it like this, and what do I do now? I can open up, I can use a plus b squared is a squared plus b squared plus 2ab. I'll do that in the next page. T square plus dt square plus twice t times dt. That's what I get for this. And I'm subtracting a t square. So subtract a t square, and in the denominator I have dt. Now I get some cancellation in the numerator. And so I'm going to get 2t dt plus dt square divided by dt. Okay, I can break this up into 2t plus, dt square by dt is just dt. All right, I'm getting the instantaneous velocity to be this. Now, dt is an infinitesimally small quantity. Okay, in fact, if I look at these two terms, this term is something I can neglect because it's an infinitesimally small quantity. If you look at the ratio between this and this, t is some time instant I'm actually talking about. This is an infinitesimally small quantity, and as I make this smaller and smaller and smaller, this whole quantity is going to approach a value which is what I'm calling as the instantaneous velocity. So this is approaching the value 2t. as dt approaches 0. So I can say that the instantaneous velocity at any time capital T is approaching to t. And the leap of faith we make is that we say it is 2t, because I'm closer and closer to this wall. I'm as close as I can possibly get. So I'm just going to say that I'm at that wall. The instantaneous velocity is approaching 2t, and as dt approaches 0, that means the limit it is approaching is 2t. So the limit is like the wall. We get closer and closer and closer to it. And so we say, well, that's where we would be if the time was, literally 0. Of course, that doesn't make sense because you can't take the ratio of 0 by 0, right? We can't literally do a 0 by 0 division, but we can do something that's almost at 0 divided by something that's almost at 0 and get a meaningful ratio. So this means that if xt, if my position is described as t square, then my velocity, and I'm not going to now write this subscript instantaneous, it's understood. It's understood that I'm talking about the instantaneous velocity. The instantaneous velocity at any time capital T is 2t. So at any time small t, it's going to be 2t. And how do I interpret this? The way I interpret this is, if I am standing here, let's say let's say this is a ski slope. Okay, I'm skiing down the slope. If I was skiing down a straight line, then I would be skiing down a fixed slope, right? I would see the same gradient for the same horizontal distance I move, I'm coming down by the same distance everywhere. But if the mountain slope looks like this, then the slope itself is changing. Because here, if somebody asks me, hey, what's the slope there? I'm going to say it feels really steep here. But once I come down here, it doesn't feel as steep. And here it's almost flat. So the slope itself is varying at different time points. And so the velocity, the instantaneous velocity, can be thought of as the slope of the tangent line at t. So if we were to draw a tangent line that cuts the graph at capital T, the instantaneous velocity is essentially the slope of the tangent line, slope of the tangent to the xt graph at that time t. And if we were to draw both xt and vt one below the other, this is xt, and if we were to draw vt directly below it, then at t equal to 0, you can see that v is 0. So we would start here, and then we would, as t increases, v increases at a constant rate. So that would be the vt graph, indicating that, indicating that the slope itself is increasing as time passes, which we can see. The slope of the tangent line, so think of a tiny tangent line, visualize at any point if I ask what's the slope, think of a really small secant line, or think of the tangent line there. That's the slope there. So slope itself is changing, and so this is really the slope function. V versus t is really the slope function for x versus t. We were able to derive the slope function v versus t from the x versus t graph. So we call the vt graph as the derivative of the xt graph. We were able to derive it from the xt graph. So we say that v is the derivative of x with respect to time. This is how we say it in English. This is how we would say it in the language of mathematics. Another way to say it is, so both v and x are a function of t. So we can also write it like this, indicating that x and v are both a function of time. So if x is t square, v is going to be 2t. And this is essentially what a derivative is. And if we have the complete position time graph, we can derive the complete velocity time graph simply by doing what we did at each point. And in fact, if we have an equation for the xt graph, we can get the slope at any arbitrary time point, a formula for the slope at any arbitrary time point by working with a general t. I could have worked with t equal to 4 specifically, and we would have seen that, well, it's 4 plus dt square minus 4 square by dt, and we would have got, so everything would have been the same. I would have got 8 plus dt. And so I would have said that the slope at t equal to 4 is really 8. Sir, how can, if it can't be 0, how can we neglect it? Um, so we are neglecting it, you mean here? Uh, we are neglecting it because, so it's a leap of faith. Okay, it's a leap of faith. We are saying that we are so close to 2t, we are so close to 2t that we can consider 2t to be the limit as dt approaches 0, right? Um, there is this well-known paradox, again from an ancient Greek philosopher called Zeno. He said that I cannot cross a stadium because to cross a stadium, I have to reach the halfway point. Then I have to look at the remaining distance and reach the halfway point of that remaining distance. Then I have to reach the halfway point of that remaining distance, and so on. And I can keep reducing my distance to the end of the stadium and keep doing this forever, but I'll never reach the end of the stadium. So this is called Zeno's paradox, uh, uh, which says that I will never reach the end of the stadium is like a limit. I can reach as close to it as I want by successively halving the time I need. I mean, the distance that I need to, the remaining distance that I need to cross. So the end of the stadium is like a limit. It's a wall. I get arbitrarily close to it, but I never actually reach it. And so the instantaneous velocity is defined as the limit. It is defined as the limit of delta t approaching 0, x final minus x initial divided by t final minus t initial. Okay, so this is the definition of instantaneous velocity. Delta t never becomes 0. Okay, dt is not 0, but we can see what quantity is this ratio approaching. What is it approaching? I'm going to define the whatever quantity it's approaching as my instantaneous velocity. Does that make sense? There's no problem in defining it this way. Whatever quantity it is approaching, that is what I'm calling as the instantaneous velocity. It's like whatever wall I'm getting close to, I can define the position of the wall. I can say that I'm getting the limit. If I keep doing that process which Zeno described, then the limit of where I would reach is the end of the stadium. I may not ever reach the end of the stadium, but I can still say the limit of where I reach is the end of the stadium. And this is how this is the definition of the derivative of any function. This is the definition, the limit, we call this the limit definition of the derivative. . And doing this kind of calculation is called derivative calculus. Well, I told you that dx and dt, those quantities are called differentials because they're very small differences. Actually, a differential really means the ratio of two small differences. Right? So each of these is an infinitesimally small quantity. The ratio of two small differences is called a differential. So doing calculations of differentials is called, calculating the differential is called differential calculus. Calculating differentials, ratio of two small differences, two infinitesimally small differences is called differential calculus. Calculus just means calculation, just like you have a calculator. Same thing. It's just calculation. Now, the word calculus is used in the context of, this particular subfield of mathematics because it's a special kind of calculation. Otherwise, the word calculus comes from the fact that ancient humans used to calculate things using pebbles. The word like calculus in your teeth refers to the deposition, like the hard deposits on your teeth. So people used to calculate using pebbles in ancient times. And so that's how the word calculate or calculus came about. Why pebbles? Because it was easier to visualize things using pebbles. Like I could say 9 is a square number because I can arrange 9 pebbles like this in the form of a square. That's a square number. Um, anyway, this is not a math class, so I don't want to get into that. But uh, we have to do a lot of practice in this. Yes. So what the kind of practice that you will need to do is to be able to see to be able to algebraically calculate the value of the derivative function for any given function, and to graphically be able to argue that as well. So, uh, for example, if I give you an xt graph that looks like this, okay, or let's say a yt graph according to Aristotle's physics for free fall motion, then then um, I can ask what is the velocity time graph going to look like for a freely falling object, assuming that, the location where I drop the object is the y equal to 0 position and the downward direction is the positive direction. All right, so again, the scenario is this is y equal to 0, this is y equal to 1, and so on. This is an object that's dropped at t equal to 0. So you see the position time graph like this. The velocity time graph, if someone were to ask that, you can find it geometrically. You can say that, well, at each point, I'm just going to see what's the tiny slope. Oh, actually, wherever I am, it doesn't matter. Any tiny slope I calculate will be the same along a line. So I expect the Vt function to be a horizontal function like that. And we can also calculate it uh, algebraically. Let's say y was given to be 10 times t. Suppose I had the algebraic description of this, then I can get the velocity function by just falling back on this limit definition, right? Write an expression for the slope of the secant line and make the time interval infinitesimally small. What's the slope of the secant line at t and t plus dt? If the y function is 10 times t, then at time t plus dt, it's going to be 10 times t plus dt. That's x final or y final in this case, minus y initial So at the left endpoint of that interval, that's going to be 10t divided by the time interval. Right? Evaluate this as dt approaches 0. So what is this going to be? 10t plus 10 times dt minus 10t divided by dt. 10t and 10t cancel out. I get 10. It's a constant value. V is a function of time, but it's ending up being a constant. That means the graph is going to be horizontal like this. So this is the velocity function which can be derived if I had the xt function. It is a derivative of the xt function. Okay, questions on this? Actually, let me do one general calculation because this rule will be very useful. Suppose my xt graph was, let's say, let's do t cubed just for practice. What would be v, the velocity function? Well, again, falling back on the limit definition, it would be t plus dt cubed, right? The velocity, the x value at time t plus dt. I can actually, this is how it would formally be written. Okay, what's the x value at time t plus dt minus the x value at time t? That's the rise over the run. That's the slope of the secant line. So you keep it like this. What is the x value at time t plus delta t? Well, it's just t plus delta t cubed, right? That's coming from the equation here. I just substitute t by t plus delta t. What's the x value at time t? It's just t cubed divided by delta t. So now I can use a plus b cubed. You must have learned this in your 9th grade or 10th grade algebra. Or you can just calculate it by default by just multiplying out a plus b, a plus b, a plus b 3 times using the distributive law. So I'll use that t cube plus 3t square times delta t plus 3t times delta t square plus delta t cubed minus the t cubed at the end divided by delta t. So once again, I get cancellations here. And notice that I'm going to get 3t square here. So let me write this down as limit as delta t approaches 0, 3t square plus 3t times delta t plus delta t square. Now, as delta t approaches 0, where is this whole quantity approaching? It's getting closer and closer to 3t square because the remaining two terms are approaching 0. So I'll just say this is 3t square. And if you were to draw the graph of x versus t, you can, one below the other, x versus t would be a graph that looks like that, something like that, right? X cubed, x is equal to t cubed. And if I were to draw the graph of v versus t, that's what? 3 times t square. So it's going to be a parabola. It's just that it's a parabola that opens, that rises more steeply than the parabola v is equal to t square. And this makes sense. Actually, on both sides, it would be like that. But let's say we don't care about what happens before t equal to 0. So I can even rub this off, or maybe just draw it in a dotted way. Notice here that if you were to consider the whole function, the slope here is steep and then it's reducing, it's becoming close to zero. Actually, it does become exactly equal to zero. The slope here is reducing, it becomes exactly equal to zero. And then the slope starts getting steeper and rising. And so it makes sense that the velocity also rises because that's the slope function. Now I can't predict whether it's going to rise like this or as a straight line or something else. For that, I need to do the algebra and see what emerges. And so I'll do one last um, calculation here for x being t to the power n in general for any n. So in that case, the velocity would be limit delta t approaching zero. I'm just writing the definition down first. X at time t plus delta t minus x at time t divided by delta t. What is the value at x at time t plus delta t? It's t plus delta t to the power n minus t to the power n divided by delta t. All right, so far I'm just plugged in the value. Now, t plus delta t times t plus delta t times t plus delta t n times. I don't need to write the whole thing down. Those of you who are familiar with the binomial theorem might be able to write the whole thing down, but assuming you haven't done that, you're not doing 11th grade math, you don't need to know that. All you need to note is that one of the terms is going to be when I select a t from here, a t from there, a t from each of these n terms and multiply them out, one of the terms is going to be t to the power n. Right? That I hope you see. The other thing you can note is that there will be, suppose I select t, I multiply a t with itself n minus 1 times, and then from the very last term, I pick a delta t. Then I'm going to get t to the power n minus 1 times delta t. Right, so let me write that down also. T to the power n minus 1 times delta t, that will be another term. But I could have picked the delta t from the first term and then the t's from the remaining terms. That would be another term. That would be another t to the power n minus 1 times delta t. In fact, I would get many copies of this. By multiplying all of them out using the distributive law, I would get only a single copy of t to the power n because I would get t to the power n when I choose this t to be multiplied by this t to be multiplied by the third t and so on all the way till the nth t. I would get a single copy of this. But think about how many copies of this I would get. Any guesses? How many copies of t to the power n minus 1 times delta t would I get? The first copy I get would be I pick delta t from here and I pick t's from the remaining n minus 1 terms. That's one way to get this. Another way I could get this is I pick the delta t from the second term, and from every other term I pick the t. That would be another way to get this. Another way to get this is pick the delta t from the third term and pick the t's from the remaining n minus 1 terms. We'll get another copy of it. So depending on where I pick which term I pick the delta t from, I would get a fresh copy of t to the power n minus 1 times delta t. There are n choices I have for where I could pick the delta t from. So that means I would get n copies of this. And I would just write this as, therefore, n times t to the power n minus 1 times delta t. Now, all other terms that follow with will have powers of delta t greater than or equal to 2. Right? Because all the other terms, when I multiply out the distributive using the distributive property, I considered the term that I get when there is no delta t. I considered the term I would get where the power of delta t is 1. There'll be a bunch of other terms where the power of delta t is 2, 3, 4, and the highest power it can have is n. I don't care about what those are, because I know that in the denominator I have, oh, by the way, I also have a minus t to the power n from here. So I'm adding that. I know that this is going to cancel out with that. And I know that what I'm going to get here is a cancellation of this with the delta t at the bottom. So I'll get n times t to the power n minus 1, right? This will cancel with this. And then other terms with powers of t greater than or equal to 2 will have one of those powers lopped off. Other terms with powers of t of delta t greater than or equal to 1. I'm just subtracting one copy of, sorry, one from the powers, because I have a division by delta t. Now, as delta t approaches 0, all of those terms are going to disappear. So this is going to be n times t to the power n minus 1. So this means the derivative of, so the derivative, so the derivative of t to the power n is n times t to the power n minus 1. So this is a more general rule. You can get all the things that we derived from this. T square, the derivative was 2t. We derived this. T cube, the derivative we had derived was 3t square. Notice that by putting n equal to 2 here, we would get 2t. By putting n equal to 3, we would get 3t squared. We can get this for any n, any positive integer n. Uh, so this is called the power rule. The power rule for derivatives. And it's very helpful because uh, you can get functions, the xt functions, to be essentially of any power, but irrespective of what power it is, if you know the power rule, you can take the derivative. Sir, is n a natural number or an integer? So it turns out that this power rule also applies if n is a negative integer, although the way I did it, um, that this doesn't suffice as a proof, because I was assuming here that n is a positive integer. Uh, but it also applies if n was negative. But the proof for that would be separate. In fact, the interesting thing is it applies even if n is a real number, like a non-negative, like doesn't have to even have to be an integer or a fraction. Could be any real number. But again, the proof of that would be uh, separate. What I showed here is not sufficient. Uh, okay. Okay, I guess should we stop here? It's probably late for you also and late for me. Any questions on what I just did here? I tried to explain what the derivative is. So if you go to your NCRT chapter and try to read about how the velocity time graph can be obtained from the position time graph, you would understand now, hopefully, what that means. Um it's although I don't really like the way this has been shown here, I think this way makes more sense. Keep one endpoint the same, move the other endpoint closer and closer. You'll see that the slope is heading towards the slope of the tangent line, and you can get it algebraically in this using this particular limit definition of the derivative. What should you read before the next class? I think the first 3 sections of the NCRT chapter, if you can go through, and if you have any doubts, you could ask about that. So 2.1, 2.2, 2.3. I'm actually not very familiar with the textbooks there. I heard that they had cut out some of the sections. There's some kind of revision that happened. But from what I saw, at least the older version, it was 2.1, 2.2, 2.3. Any doubts or questions about what I did? I know this started out as a little easy for some of the students, and I think most of them have already logged out. But like I said, everyone's Goldilocks zone is different, so it's impossible to cater to people with a wide variety of different backgrounds. But you can always stop me and ask me if something's too hard. Maths for JE. So my time is kind of limited, so I'll leave that to Kapil. I mean, I'm happy to teach calculus if needed, but since I've been asked to teach physics, I'll just teach whatever bare minimum is required to handle physics. All right, thank you all. Good night.